Okay, finally, we are going to look at Advanced Encryption Standard, AES. So this is the current data encryption standard. It was, excuse me. Okay, so it was devised by three cryptographers or mathematicians. Okay, it was initially called the Rindale. Okay, and so this algorithm was selected to be the AES in 2001. Okay, so AES AES is not following Feistel's cipher scheme. Okay, so it uses a different scheme, but it still has multiple rounds and using multiple round keys. But it is not simply based on exclusive OR and substitution function F. Instead, it is based on finite field operations. So as we mentioned earlier, so this is a byte level. Okay, so this is a byte level operation. So the operations are operated on bytes, which is 8-bit long, and it's a finite field. It's called Galva field, GF 2 to the 8. This was first studied by a French mathematician called Galva. Okay, that was Galva. So the things here is each byte is represented by a polynomial of degree 7. So this is a byte. So this is represented by a polynomial. So this is a unique representation. P1x P0. And you can then define multiplication. You can then define addition. So addition is the same, exclusive OR. So this, and subtraction is the same. Okay. And then you can define multiplication and inverse of multiplication. So this is division. So division is harder, which has to do something with, has to do with something called irreducible polynomials. But as I said, we don't need to worry about how these are done. We just need to take granted when we look at these operations that we know that there is a strong mass behind these operations. Okay, so that is one thing. The second is that instead of a fixed key length, AES supports 3 different lengths. One is 128 bits, the other one is 192 bits. The last one is 256 bits long. So for anything that requires strong confidentiality, you can then use 256 bits. For normal applications, 128 bits probably would be good enough, for instance, for wireless communication. Okay, so in the chapter 6, we are going to talk about this. So we're going to come back again. And then the block size is 16 bytes. So that's 128 bits long. And so instead of represented a block using a linear string, we are going to represent it using a 4x4 square matrix. Okay. And to represent this 16 bytes, so 4x4 16. So so this is 4x4. So we got A00, A01, A02, A03, and then the last row is A30, A31, A32, and A33. So this is 4x4. Each of these Aij is a byte, so you got 16 bytes. So that is your block. So it uses 4 simple operations, okay, on this state matrix. So this is called a state matrix. And we use 4 operations to operate on this state matrix. So let me now remove this and then move on to the next slide. Okay, takes a while. Here. Okay, so these 4 simple operations are the following. Substitute bytes, we call it SUB. Shift rows, called SHR. Mix columns, MIC, and add round keys, ARK, ARC. Make ARC, okay, sub, shift, make, and ARC. Okay, so substitute bytes is a nonlinear operation based on a defined substitution box. Now, remember we said that these operations are on this Galva field to the x power. So because this is field, we can have inversion. So we can define a invertible substitution box. Okay. So this is used to resist cryptanalysis attacks and other mathematical attacks. Okay, and shift rows is simple, it's a linear operation, and this is used for producing diffusion. Mixed columns is also elementary operation, and it is used for producing diffusion. And then we have these add round keys, which is has something to do with keys. So this is used to produce confusion, and this is linear. Mixed columns use mixed columns. This mixed column operation uses lot of, or quite a bit of finite field operations. Okay, so here is a diagram. So plain text comes in. You first generate, okay, we use AES 128 as an example. So this is AES 128. So it has 10 rounds, and it would need to use 11 keys, subkeys. Okay. All right, so we got 11 subkeys. And so your plain text comes in, you first confuse, you first use the first subkey to produce some kind of confusion, and then the output of this going to be the input of round one. So round one is a sequence of sub, shift, make, and arc. So repeat this, okay, until round 9. So round 9 is still the same number, same sequence of operations. But in round 10, the operations are different. So then you get a ciphertext. Okay, so decryption is not completely symmetrical. Okay, so so ciphertext comes in, the same thing. You use the 11th key, but then here the ordering of these operations are inverse shift, inverse sub, arc. Inverse arc is the same as arc, so because it's exclusive OR, and then inverse make. So it's not in the same orders as encryption. So you do the same sequence of operations for 9 rounds, and then in the last round, you have inverse shift, inverse sub, and then arc, which is also not exactly the same order of the encryption. So this is at a higher level. This is a higher level view of AES. So now let me remove this marking. Okay. Okay, so AES S-Box, AES S-Box is a 16 by 16 matrix built from operations over finite field GF of 2 to the 8th. So what it does is it is a permutation of all 256 elements. Okay, so each element and its index are represented by 2 hexadecimal digits. Okay. So now let me do an annotation a little bit. Okay, so this is 16 by 16 S-Box. Okay, so so we got 16 rows and 16 columns. So then each of these is a 4-bit number. And we are going to use a hexadecimal hex to represent it. Same here. For each row, for each column is also a 4-bit number. Okay, 16. And then for each element, because you got 256 elements, so each element is a byte. So this is a byte. and then it's going to be represented by 2 hex number. Okay, the first 4 bits is 1 hex number. The second 4 bits is another hex number. So that's what this matrix is. So this matrix, let's call it S. So S is invertible. Is invertible. Okay, it has an inverse. So this matrix has inverse. Okay, so what is this Bytes substitution function? Okay, so we let W be, now I start with B0, okay, B7 be a byte. So we define a byte substitution as, function as follows. So we take the first, so this will be my row number, and then this will be my column number. So Sij from this matrix, okay, so this is 16 by 16, that's S. So that element is the substitution, that's the value of this input. So this is the input. Okay, the output is Sij. The element at the ith row and the jth column. So, if we call this input W, then that's what this means. So it has inverse, so inverse on W gets, sorry. So I should say the inverse on Sij, it gets you back to W. So that's what we have. Okay. So now let me see if I want to erase all this marking using undo. Okay. Not as convenient. So let me just do this. Move down. Move down. Okay. Then let's see add round keys. I'm sorry, let's see key generations, round key generations. Oh, so looks like this, so this should be, so this, so this should be this. This should be this. So this operation is actually defines, so this is a number. Okay, so this is represented by a polynomial. Let's call it f of x. Okay, so this number is f of x. That's a polynomial. These are the coefficients of that polynomial. And this m really defines x times f of x. And this small mj defines the operation of x to the j's power. Okay, so so we don't need to worry about the underlying math to come up with this form, but what we just need to take is to take it as granted. So if B7 is 0, it is a left shift, right? So this is left shift. Otherwise, if B7 is 1, it will be left shift first and then exclusive OR this. So this is a irreducible polynomial. That means so these are coefficients of a reducible polynomial. What that is x, fourth power, plus x cubed, plus x plus 1. Okay, so this is so we just take it as granted. So again, for this Sj, you apply this capital M because this x multiplies itself for j's times. So you get this multiplication, right? So if j is 0, that's just number 1 because x0 is 1. If j is 1, it's just x itself. So this is number 1. So this is x. Otherwise, it will be equal to x times x to the j minus 1. So that's why you use capital M. So that is for x times, let me use this symbol, x to the j minus 1. Okay, so that's how you define these two basic, how you got these two basic operations. So what we want to see here is how these subkeys, round keys are generated. So we first define this TW comma J, and W is a byte, okay. I'm sorry, no, it's not a byte, it's a, yeah, W2 is a byte, but your input, your W is a 4 bytes long string. So we call this W1, W2, W3, W4. Actually, I have it here. Okay, so what you want to do is you apply S substitution box on S2. And then you apply small m on, so exclusive OR of small m of j minus 1. So this j is right here. So, and then you concatenate S of W3, S of W4, and S of W1. So that's what this T is. Okay, so just to make it fairly complicated, but the execution itself is efficient. But when you want to do analysis, it would be very hard to do. So now let me erase this to move on to the next slide. Okay, now we put these things together to generate round keys. Okay, so this is a 32-bit. So our key is 128 bits long. So let me put it right here. So we have our key, 128 bits long. So we can divide it. We can divide it into 4 segments. The first 32 bits is the first segment. And then the second 32 bits, the third, and the fourth. Okay, so this then is going to be, as you can see here, so this will be W0, W1, W2, W3. So from now on, I'm going to define WI because I want 11 I want 11. So this is already the first key. So then I want 10 more keys. So that means I want 44 many such WI. So that gives me 10 keys. 40 many, not 40, 40 many. Altogether is 44, but this already, 4 is already counted here. So for this is how it is defined. So WI is equal to W. If I is divisible by 4, then this WI minus 4 exclusive OR this function T. So now this is where it is used. And this is I divided by 4. Otherwise, you just exclusive OR the WI minus WI minus 4 exclusive OR WI minus 1. So that's how it is defined. So finally, we then have the 11 round keys defined in this way. So let me now remove this. We can move on to the next slide. Okay. So add round keys, just exclusive OR. Okay, so simple, byte-wise exclusive OR. And as we know, exclusive OR, the inverse of exclusive OR is exclusive OR itself. Okay, so hence this is arc inverse is arc itself. Okay, substitution, substitute bytes. We just apply the substitution function S on each element is inverse, applies the inverse of S. So this is also easy to understand. And then we have this, because this is inverse, so we have this sub on sub inverse of A gets A itself. Likewise, sub inverse on A, then you get A back. So shift rows is pretty straightforward. So what you do is you shift each row starting from row 0, left shift for 0 times. So starting from row 0, or if you think of this as the first row, then you shift it for 0 times. Okay, so this is the second row, you shift it 1 time, left circular shift. So that's how you get this result. So likewise, the inverse will be the right shift, right? So circular right shift again, you shift it back. So that is simple. Okay, mixed columns would be the most difficult, most complex operation. So, but each operation here, we have already defined. So we already defined the capital M, and then the rest of it is exclusive OR. It's just the positions you apply this capital M would be different. So this is for the first row, second row, third and fourth row, right? So this is how you do. So these J is from 0 to 3. All right, and the inverse. The inverse, now this is a nonlinear operation, obviously. So the inverse, you got to say is a n cube. And so don't worry about the math here. We just take it as granted. So then the encryption and decryption is as follows. So, so this is just the encryption. Let me do some annotation a little bit. Okay, so this is the first subkey you use, and then you repeat the same sequence of operation for 9 rounds. So substitution byte, shift rows, mixed columns, and add round keys. And the last round, round 10, is different. Decryption, you also, in a similar fashion, but it's not symmetrical. Okay, so the operations are all inverse, but then it's not the same sequence. So for 9 rounds, it applies the same sequence. So not the same sequence as encryption, but for decryption, it repeats 9 times of the same sequence of operation, and the last round is different. Okay. Here is a correctness proof of decryption again. We use mathematical induction. The proof is fairly straightforward. So what we want to show here is that for any I from 1 to 10, we want to have CI, which is equal to shift rows, substitution bytes, and then A sub 11 minus I. Okay, so once we have this, then we can show that C11 is indeed a 0. Okay. Okay, so assuming, now let's say we're assuming this is true, then let me do an annotation. Then we have, because this is what we want to show for decryption to work. So we know by definition, C11 is the last round is add round key, substitution by inverse, shift row inverse, and on C10 and K0, because we use, when we apply these round keys, we use the inverse order. So now C10 is equal to, assuming this is true, we know this is equal to shift row, and then substitutes bytes, A11 minus 10, C10, okay, so then that's A1. So let me put it here, A1. And then we close this parentheses, we got 3 more. And then add round keys. So that's equal to this. Okay, so these two cancel each other out. After that, subs cancel each other out. After that, what we are getting, so sorry, we don't have this. Okay, let me rewrite it again. Okay, so I'm going to say these are add round keys. So we're going to put this in first. So this is a sub C10 add round keys. And then this is sub inverse, shift inverse, I'm sorry, 10 is equal to shift rows, which is, and then substitute bytes, and then this is A1, 1, 2, 3, exclusive or K0. Okay, so let's cancel each other. And then we got sub A sub 1. And let's cancel each other. So we got A sub 1, K 0. Okay. And then A sub 1 is equal to A1 is from A0 in the first round. So that's A1. So this is A1. Okay, so then we know these cancel. So we get A0. Okay. The same thing exclusive or itself. K0 exclusive or itself is 0. Okay. So that is why. Okay, if we prove this, then we can show the correctness of AES decryption. So now let's see how we do induction proof. So I is from 1 to 10. So let's look at when I is equal to 1. By definition, okay, C1 is equal to A11 comma K0. So this is the inverse round keys, inverse order of applying these round keys. So this is then A11 exclusive or K10. So A11 is obtained by this. Okay, so this is the last round. So this is the last round. That's A11. So here, if you rise things up, that you put this at round key into here. So we get this. So this and that is the same. So, and then these two K10s the same. So that's canceled. So what is left is this part. So then we know when I is equal to 1, this equality holds. So this is the induction base. So now assume that for any I, okay, greater than equal to 1, less than equal to 10, it is true, then we want to do induction step. So that's, so this should be strictly less. Okay, so get rid of that, strictly less than 10. So then we do C sub I plus 1. So this is when I is less than 10, we know we have these 4 operations. Okay, we have 4 operations. And so this is a 9, this is a round 1 to round 9, right? So then we know this is the sequence of operation with this round key. So because of Ci is equal to this, so this is Ci is this. Okay, replace Ci with this by hypothesis. Then you can see this is shift canceled. After that, this is sub canceled. So what we're going to have is A11 minus I, and then add round keys. So here, so this one should be, when I have exclusive OR here, so this should not be there because this has been exclusive OR. So that's what we are getting. Okay, so it's not there, sorry. And So that's make inverse of A sub 11 minus I exclusive or K sub 10 minus I. So now we are going to replace A sub 11 minus I from the encryption. So that is obtained from this part. So that is equal to this. Okay. So you remove this R add round key, you get down to this. Okay, so this and that is the same. So now if you see here, this is these two cancel because they are the same, and these two cancel. So what we left is shift row substitute bytes A10 minus I. So A10 minus I is equal to A sub 11 minus parentheses I plus 1. So hence, this hypothesis, this induction step holds. Hence, this is true. Because if this is true, then we know that C11 is A0. So this is the original plain text. And this is C. So, so that means, I'm sorry, this is not C. So this is this is equal to, so this decryption, which that's C11, and that is equal to M. Okay, so now let me remove this. And then we can move on to the next slide. Okay, so we already done this part, and that is AES.